So I'm going to record the sessions here. We'll have breaks throughout. I mean, it's a very long session. It goes from 11:30 to 6:05 p.m. So 6.5 hours, more than 6.5 hours. So it's pretty long, but we have a lot of material to cover. I mean, for this first week, I want to go through 6 chapters. And so we'll be plenty busy. And so I'm going to send out a survey and just we'll get more familiar. I know some of you are probably already familiar with Canvas and maybe Piazza, but let me go through the course mechanics first and then show you. First off, Piazza. If you haven't joined, I sent out a link to your El Camino email. And so far there's, I think, 17 people haven't joined Piazza, but I'm going to post things here, handouts and other stuff on Piazza. It's just easier sometimes than posting on Canvas. And so make sure you sign up for Piazza. I think I'm the only class from El Camino that's on Piazza. So if you go there, you aren't going to have very many options to sign up for a summer session class here at El Camino. You'll just need the access code. The access code is Chem4, no spaces, all lowercase, and that'll get you in. And so on Piazza, what I have is I have the handouts here. These also on Canvas here, but the syllabus, let's go ahead and click on that and we'll take a look at the syllabus. So this is it, this 6 weeks, we're going to cover 19 chapters in 6 weeks. The pace is pretty fast. 6 chapters, and then maybe it slows down a little bit. So this first week is a lot. Normally what we do is we break up the session. So it's 6.5 hours, so we'll have some lecture and then some lab. But what I want to do is I want to do all the labs that we normally do in the summer. And we're going to do those as kind of a demo. But you'll be collecting the data. And so these are the actual labs we're going to be doing. I'll have some assistant to help me. This is a dry lab here. And so in blue are the labs. So the first 2 weeks, we're going to have no labs here. And then I crammed in all the labs in the last 4 weeks here. And so the first 2 weeks are heavily lecture intensive, and then we'll have some labs in there as well as we go on. And so here, if we look at the first week, we're going to be covering, chapters 1 through 6. And then when did I put the exams? Yeah, we're going to spread out the exams. So the first exam is going to be next week on Tuesday. Here, exam 1. Exam 1 is just going to cover probably the first, 5 or 6 chapters. Probably the first 5 and part of 6. And it's a lot of homework in chapter 6, so it's not you're not gonna have all of chapter 6 there. And then the next, we're gonna have 3 of these midterm exams, and so every 2 weeks. And so this exam 2 will cover through, let's say, chapter 12, maybe part of chapter 13. And then exam 3 here. Exam 3 and the final exam are in the same week here. Exam 3 is going to cover probably through chapter 18, and then 19 will be on the final. The final is going to be comprehensive. We'll cover the entire course from the beginning. Okay. So that's the syllabus. That's all 6 weeks here. There's some important dates to keep in mind. Thursday is the add or drop deadline. Here, blow this out. I have the little footnote here, this footnote, like chapter 3, and then footnote 1. And so let's go to footnote 1 here. Footnote 1, additional required reading is found in the Chemistry 4 supplement. And so the book, for some sections, doesn't go in deep enough detail. What we want is we want a smooth transition in going from Chem 4 to Chem 1A. The Chem 4 book is pretty high level for a Chem 4 book, but our Chem 1A book is on the higher end of the spectrum in terms of rigor and depth and intensity. So we try to have a little intermediate step there. And so that intermediate step is some of the supplemental reading that you're going to find in the Chem 4 lab manual. And they'll make the transition to Chem 1A a little easier and not such a big step up. And so you'll see that footnote here. So there's some supplemental stuff on measurement, on gases, on nomenclature, etc. A lot of these chapters will have it. All right. Another important date is this one here, August 7th. August 7th is the last day to drop with a W, withdrawal. Otherwise, if you don't drop by this date, you have to just take the grade, whatever grade you get at the end, of course. The labs, I know these are all for you going to just be on screen. We aren't actually going into lab, unfortunately, unless something drastic changes. These are just going to be video labs, experiments, but we'll do these real time, and we'll collect actual data. And so we're going to go through the whole process here. Safety, even though you aren't doing these, you have to be aware of the safety rules. And check-in, if you're going on in Chem 1A, they're going to expect you to already know how to check into the laboratory. So we'll go through that process and do these. Some of these labs, I'm going to shorten them, to make it fit our schedule. Okay, we'll see. Okay, I actually do more labs in the regular term, fall and spring. The summer is a little short, so there are a couple of labs that I eliminated here. But these are the required ones here. All right, so we're meeting the same schedule every day here. And so pretty much what I'm going to do is I'll probably talk for an hour, and then we'll take a break, and then go for another hour, and so on. All right. Move on. Here. Okay, the other thing you're going to find on Piazza and also Canvas is this course info sheet here. This came out poor resolution, sorry. This is just taken from our course catalog, but it just tells you what the course is about. If you're ever on campus, my office is in room Chem 120. And here's my phone number if you need to contact me. This email, my El Camino email, is often full, and I can't respond to it. Our El Camino email boxes are so small that what I did was I made a new email. And this email, I prefer that you use my Gmail account here, especially when my El Camino email becomes full. I might not get back to you for a week while I clean it out. And so this, you'll get a much more rapid response here. You can also leave me a voicemail on my phone here, extension 3240. Okay, so I prefer you not to use this. Awesome. Right, so what we're studying is chemistry. So here's the dictionary definition of chemistry. We're mostly interested in number 2 here. I like this definition the best, but I still would change it. The composition, structure, properties, and reactions of a substance. What I'd like to do is, if I could change this definition, I would write, something like this. I'd write the composition. Let me see. Okay. I'd probably eliminate this here and just say the composition, structure, and properties. And there are two types of properties that chemists are very interested in. One type of property, and I'll talk about these again today, but one type of property are the physical properties. Physical properties examples would be like melting point, and boiling point, density, those types of stuff. And physical properties we use to characterize matter, like gold. You know, gold has a very high melting point and very high density, you know, whereas aluminum has a much lower melting point and a much lower density. So those are physical characteristics of the material. But there's also another type of property, you know, the other type of property is called a chemical property, you know. And so, you know, two types. One would be the physical. Sorry, I have to get used to writing on a tablet again. So if you can't read what I wrote, then stop me, let me know. And the other type of property are the chemical properties. The chemical properties, these are chemical reactions. And so when a chemist thinks about properties, they think about both physical properties and chemical properties. But in terms of this definition, you know, they're labeling properties as strictly physical and then adding reactions to indicate that these are the chemical properties of it. Whereas for a chemist, it would just be the composition, structure, and properties, both physical and chemical, of a substance. Now, substance, you know, we look at substances, you know, when we think about substance, there are two types of substances that we look at. Usually these are pure, you know, we have different things, but it need not be pure. You know, substances could also be a mixture, like gasoline, you know, or mixture. But normally when somebody uses the word substance, they're implying it's pure, you know. But in this case, we're interested in mixtures too. There are lots of mixtures that are very important for, just one second, so I'll be right back. Oh, yeah. Yeah, sorry about that. But here, getting back to this, so in this, I'm taking it that they're indicating that the substance could either be pure or a mixture. You know, common mixtures would be like sugar water. You know, chemists are interested in sugar water or salt water, you know, because at different concentrations will have different properties. For example, for biology, you know, there's something called isotonic saline, you know, which is an important mixture, you know, for IVs, you know. So there's a little bit more, you know, it's not as rigorously defined in this dictionary, American Heritage Dictionary, as a chemist would have it, you know, the wording here. And so taking this substance, you know, when a chemist uses the word substance, they're usually implying it's pure. And a pure substance would be like pure salt, not like a mixture like salt and water, that kind of thing, but just, or pure water, you know. And so that's the usual implication there. So, you know, what we could say here is the composition, structure, and properties, rather than maybe this, because you know, it's not being strictly defined as a chemist would do it. And in terms of strict definition, I'd probably use the word matter here instead. And then this is all encompassing. You know, matter can be pure, it can be a mixture. You know, and normally when we're looking at pure substance, you know, pure substances like pure water, you know, as you know, something like water is H2O. And so something like a pure substance like water would be labeled a compound. A compound because it contains what we call elements, you know, the element hydrogen, element oxygen in a fixed ratio, fixed composition here, like that. Or it could be like gold. Does anybody know the chemical symbol for gold? No penalties for guessing. Go ahead and give it a guess.
AU.
You know, these, I think of Latin is like orium. Orium is Latin word for gold. A lot of these symbols come from that, you know, and so that's correct. Khazra would be right, except the U, if it's capital U, it should be lowercase u, because if it's capital U, it could be mistaken for uranium. Uranium is U. But, and so that's minor. And so this would be gold, and that would be a element, you know, element. And so normally when people talk about substances, they're talking about either a compound or an element. But, you know, our world contains lots of mixtures like air. Air, you know, is there such thing as pure air? You know, well, when we're thinking about pure air, well, what does that mean? You know, and so if somebody were to let's say bottle it and sell it as pure air, this is 100% pure air. You know, does that have meaning? Something that does have meaning would be like 100% pure oxygen. If we had 100% pure oxygen, then there shouldn't be other stuff in there mixed in. But, you know, the air that you breathe here, you know, you might say, you know, LA has the purest air on earth, but, you know, somebody else might dispute that. And they might say, you know, well, you know, no, I disagree. Maybe San Francisco has the purest air on earth. And then somebody else might say something else. But the problem with air is air is a mixture. So mixtures, you know, it's going to vary. The air in Los Angeles has a different composition, different makeup of, you know, air. Do you know what's in air? You know, the air that you breathe. Does anybody know what that mixture consists of? Not like the two most common things in air. Well, air, there's a lot of empty space. The last two are correct. Khazra, it's not, there's very little hydrogen in the air. Even though hydrogen, it turns out, is the most abundant, you know, what we call element. Element, these are the building blocks of matter, like, you know, hydrogen. Our bodies have a lot of hydrogen, but not hydrogen in what we call elemental form, but hydrogen in compound form, in the form of water. So our bodies have a lot of hydrogen. And they have a lot of hydrogen by what we call atoms, not by mass. The hydrogens don't weigh much. The smallest piece of a hydrogen is an atom. And so I just need to send out the survey to see, you know, how familiar you guys are. I'm just assuming that, and if you don't understand something, let me know, you know, when we get there. But nitrogen's the most abundant species. Air is about, you know, 78, 80% nitrogen, and about 20%, 21% oxygen, you know, depending on how precise you want to be. But it's mostly nitrogen and oxygen. And so the amount of oxygen will vary, you know, and there are other components of the mixture that will vary as well. The humidity, you know, the amount of water vapor, other stuff. So air is a mixture, but still chemists are very interested in air. And so this is why I crossed out substance here and wrote, you know, matter, because matter can encompass all these. Not only can it encompass all these, but it can encompass the parts, you know, that gold are made out of, you know. The smallest particle of gold that you can have would be one atom of gold. And the atom of gold would be just like this spherical particle like this. And if you try to break up that atom into even smaller pieces of gold, you'll be unsuccessful. What happens is if you try to break up this atom into smaller pieces, you get something called subatomic particles. And these are the particles that make up gold. And those particles for us would consist of things called protons and neutrons and electrons. Okay. And those particles themselves can be broken up into smaller particles called quarks. But we aren't going to get into that. But what happens is if you take this single gold atom, you know, and try to break it into a smaller piece, it's no longer gold. But chemists are interested in subatomic particles too. Subatomic particles are matter. In fact, what is matter? You know, how do we define what matter is? You know. So let's talk about matter for a second. Does somebody have a good definition for matter? Or how about a bad definition? Does somebody have a bad definition for matter? Or any definition, just a guess? Okay, that sounds good. Let me make sure I pronounce Maniza. What was it? Can you pronounce your name one more time? Sorry. Maniza? Maniza.
Yeah.
Maniza.
Yeah, that's correct.
Okay, thanks, Maniza. Yeah, that's correct. Anything that occupies space and has weight. But weight is very tricky, you know, because, you know, can you be weightless? Is it possible to be weightless? Yeah, it is possible to be weightless. So if you become weightless, does that mean you're no longer matter? No. And so this is a very subtle thing. Rather than using weight, is there another word that we could use in place of weight that would make it, you know, it doesn't matter if you're in a weightless environment. You know, there's airplanes that go up, you know, to quite high altitude, and the occupants can become weightless. They can float around, and you know, they can spill water, and when they spill water, it just floats in front of them. You've seen that. It's pretty cool. And so density, yeah, density would work, but the better one would be mass. Yeah. And so Anthony has it right, mass. And so we want matter should occupy space and have mass. All right, so you could be weightless, but you could still have mass. Mass is, you know, what mass is the quantity of matter. And so the more massive something is, the more matter that you have. And so we use different units for mass. You know, weight we usually use pounds, you know. Mass we usually use kilograms. And so an example of this would be, you could be, let's say, 100 pounds on Earth, but you would be, actually I shouldn't have done 100. You could be 100 and let's say 120 pounds. You know, if you're 120 pounds on Earth, do you know how many pounds you would be on the moon? Would you be 120, if you're 120 pounds on Earth, would you be 120 pounds on the moon? It turns out that looks like the consensus is no, and actually you wouldn't be 120 pounds on the moon. Do you know how many pounds you would be on the moon? If you're 120 pounds on Earth, how many pounds would be on the moon? Well, it depends. If you've had physics, then yeah, you probably can answer this. Yeah, very close. Yeah. Well, let me see. You know, your weight depends on the gravity, you know, the gravitational. That's why if you go into zero gravity environment, like on the aircraft or out in space, you know, there's zero G or zero gravity or very negligible gravity, we can say. The gravitational pull on Earth is pretty strong, and that's what holds us to the surface of the Earth. The gravitational pull on the moon is a lot weaker. It's about 1/6, as I recall from physics. So if you're 120 pounds and you divide it by 6, that results in 20 pounds. You'd be 20 pounds on the moon if the gravity is 1/6 that on Earth. And so that's just 120 divided by 6. Or times 1/6, you know, the gravitational pull. And so, but let's say you're 120 pounds. 120 pounds, how many kilograms is that? And so I have my calculator here. Actually, I recommend this calculator here or the equivalent. Don't go for the cheapest calculator. Go for the next level, the second cheapest calculator. But let's say if you're 120 pounds, then what I do is I'll just convert that into kilograms. And it's easy to convert because they're like 2.202 pounds per kilogram. And so that ends up to 54 and a half, or roughly 54 and a half kilograms. So if you're 54 and a half kilograms on Earth, are you 54 and a half kilograms on the moon? Yes or no? If you're 54 and a half kilograms on Earth, would you be 54 and a half kilograms on the moon? Okay, it looks like the consensus is no. There's one yes here. Are there any other yeses? Okay, and Sarah has it right, actually. If you're 54 and a half kilograms on Earth, you would be 54 and a half kilograms on the moon. The kilograms, that doesn't change because the difference between weight, which would be pounds and ounces, weight is the gravitational pull on your mass, you know, versus mass. It's a subtle difference versus mass. Mass is just the amount of matter. Weight is the gravitational pull on the amount of matter. And so for weight, we definitely need gravity pulling down on that, whereas mass, we don't. It's a little tricky, and we aren't really going to get into this subtle distinction here, but just in the back of your mind, you should know that weight and mass aren't necessarily the same. And even though we say, go weigh this or go weigh that, in chemistry, when somebody says go weigh something, they're asking you to determine its mass, not its weight. People want to know its mass. Fortunately, it's not a big deal for us because how often do we go out in space? Not really. And even if let's say we work in a tall building, you know, let's say we work on a 10-story building, 10 floors. If you're on the first floor and you go up to the 10th floor, you know, so you're a first floor lab, you go up to the 10th floor lab, the gravitational pull on the 10th floor is a little weaker, you know. The gravitational pull is stronger as you get closer to the center of the Earth, but it's negligibly weaker, you know. And so here, the force of gravity versus the force of gravity here is negligible. Whereas if you go, you know, up into the atmosphere, then you're going to start to see a little difference, you know, in there. But for us, you know, the weight is fairly constant because we aren't going to the moon. You know, it's not like tomorrow we're going to go to the moon. And so chemists use these interchangeably here, which physicists wouldn't necessarily do. But just keep that in, the distinction in here. So matter occupies space and has mass. But, you know, chemists don't only study matter. And so this is well, since we're interested in matter, you know, what is not matter? If it occupies space and has mass, isn't that everything in the universe? Seems to be everything in the universe. So what doesn't qualify as matter? Is there anything that doesn't qualify as matter that you can think of? What is not matter? Well, there's antimatter, but, you know, we aren't going to really get into, in chemistry, we aren't going to, in nuclear chemistry, we'll be talking about antimatter. But for us, we don't worry about antimatter. And so if it's not matter, what is it? Give me one example of something that is not matter. Can you give me one example of something that's not matter? Gases, okay, like air. That's a pretty good one there, but it turns out that gases do contain matter. And so if you take your hand and wave it, you can feel the matter here, you know, the air. Or you can fan yourself. When you fan yourself, you can feel the air hitting you. And so that's actually matter. Space, yeah. Space, though, if you're trying to fan yourself in space, then nothing's necessarily going to happen. Or this inside the middle of this is supposed to be something called a vacuum, and a space is a vacuum. And it's where you suck all the air out of it. And so this is a thermos type mug where they tried to suck the air. It's hard to suck all the air out, but in space, there's nothing there. So empty space is what we call a vacuum. And so if it's not matter, then it's empty space. Empty space. Empty space is not matter. Even though empty space occupies space, well, you can change the amount of space. There's nothing in it. It has no mass. Mass is an indication of how much matter you have. And so if it doesn't weigh anything, here we are using it interchangeably, then it's empty. So empty space. Sound, actually, does sound travel through space? You know, we know sound travels through air. There's no problem. Does sound travel through water? Can you hear underwater? Yeah, actually, does sound travel faster underwater, slower, or the same speed underwater? This is physics again. This is not a physics class, but Carlos, you say slower. Does anybody say faster or the same? The same speed, slower, slower. Okay, so Marquise, Kazra, Corinne says the same. These slower. Oddly enough, it travels faster, you know, through water. This is weird. Yeah, water is more dense, right? Air is a gas, and the reason why I said gases, that's pretty good for empty, for something that's not matter, is because gases consist mostly of empty space. The particles of gas are very small, and so gases are mostly empty space, and so you can compress them and expand them. But yeah, it's because of the density there. You're right, Kazra. But what about in a vacuum? You know, empty space is called a vacuum. And so the sound travel in empty space, let's say you're on outer space and there's just a vacuum there. The sound travel there. What do you think? No? Anybody else? Or don't know? Yeah, actually, it doesn't. Sound will not travel. Yeah, there's no vibrations in the air. Yeah, sound is caused by the vibrations in the air or the vibrations in the water molecules. It's that. And so sound requires matter. You know, otherwise, if there's no matter present, then you aren't going to cause these vibrations. Like if I knock this table, you can hear it. You can hear the sound from that. You can feel the vibration in the table, you know. So we'll think of something else. Is there something else? There's empty space, which is a vacuum. Empty space equals a vacuum. vacuum. That's supposed to be an M, the end. And so this is not matter, not considered matter. But the funny thing is, do chemists study vacuums? What do you think? Do chemists study vacuums? Yes. So yeah, this I like this definition, but chemists do study empty space vacuums. The reason they do that is they, if you have a vacuum, there's nothing in there, so it's very clean, and so it helps for certain things. So people were trying to grow things out in space, or vacuum chambers. They try to mimic, empty space on Earth by using these vacuum chambers. And they don't want things there interrupting things like, there's an incredible vacuum that they get from the Large Hadron Collider in Switzerland. And so this is a big topic. I'll come back to what we're looking at, but it's like UHV technology. Maybe we'll go UHV vacuum. So they build all these trick chambers like this to try to mimic outer space on Earth here, by sucking all the air out of this. They need these are built like submarines. They have to be built like submarines because do you know how much air is weighing down on you? Do you know how many pounds per square inch of air weighs down on you around sea level? Like about 15, 14.7, 15 pounds of air that you're swimming in right now. And so if you suck all the air out of here, then you have, 15 pounds trying to crush this. And so these are built like submarines so they don't implode, here. They got these very thick windows like submarine windows here. And this is what we call ultra high vacuum here. The chemists spend a lot of time looking at it. They want ultra high vacuum because they want to suck out all the air, out of these. Large Hadron Collider has an atmosphere that's comparable to the moon. It's very hard to generate this. Let's go back. Here. Where was it? Okay, here I was. So, even though I wrote matter here, chemists are very interested in empty space vacuums. Not only that, chemists are very interested in another thing that's not classified as matter, because, empty space is going to have an impact on certain things. Try to adjust this, or it was before. On things called synthesis and whatnot. And also accelerating particles. They're trying to get particles to collide in these particle colliders. They want vacuums. So chemists are very interested in vacuums. Chemists are also interested in something that's not considered matter as well. So not matter, one, it's empty space here. You should have gone with a different color maybe. And two, one, empty space, and then two is light, light. I'm using light in a very general term because what do we consider light? Light is what's termed as EM radiation. Does anybody know what EM stands for? EM radiation. Yeah, electromagnetic. Good, Catherine. Electromagnetic radiation. And so what's light? Light from the light bulb is light. That's light. But also things that are unexpected, like radio waves. You know, even though sound you need a medium, but will radio waves travel through empty space? Do radio waves travel through vacuums? Yeah, and the answer, that's correct. Radio waves will travel through vacuum. And electromagnetic radiation does. And so we're interested in this, even though this is not considered matter, this is considered energy, you know, energy in form of light, you know, radio waves, X-rays, gamma rays, visible light, that's all light or electromagnetic radiation. And the reason we're interested in this, even though it's not matter, is because this is going to impact matter. You know, if you turn off the light, are there any colors? You know, if the room is dark, do you see any colors? Let's say there's no light. Would there be, let's say this is blue shirt here. If there was no light, would this be a blue shirt? Yeah, it wouldn't. We need the light. The light interacts with the matter. You know, the white light from the light bulb interacts with matter and makes this blue. If there was no white light, there'd be no blue. And so we're really interested in this, even though this is not considered matter, these have an impact on matter. And therefore, since we're interested in matter, we want all things related to matter. So we do study vacuums, empty space, and we do study light, electromagnetic radiation or energy, and its interactions with matter. And so I just want to be more concise in this definition here of chemistry here. And we're going to be talking about that more as we go along. And so let me clear this here, and then we'll just move on here. But let's see, it's 12:27. We'll take a break shortly, but here. So I have the course objectives here. You could read through those. You know, let's see what's going on here. My mouse, there we go. We have something called SLO, student learning. There's lots of learning objectives here, too many to list. So this is it. Required materials here, the book. Now, there were some questions about, do you need OWL? You don't have to have OWL, but OWL, I think, has the e-text bundled with it. And so the e-text comes in very handy to have. That way you don't have to have the book always. I'll show you what the e-text looks like. You do need this though. And so some people I know rented the book, which is okay on Amazon. They didn't get the OWL bundle, but that's okay as well. Anyway, this is a good book to have. So if you bought it, it's a useful reference for Chem 1A too. This you'll definitely need, and you'll have to get this from the bookstore. For calculators, I recommend if you're going on to Chem 1B that you get something like this. You know, it doesn't have to be this brand, but this is the calculator I use. It's the Casio FX115X, and so this was the next level up. And so the cheapest calculator was about $10, and this one was like 15. Well, I bought this one at Target, and so I got the little discount, plus it was on sale. So I got it for around 15, but $15 to $20 is what people spend for this. Now, the good thing about this calculator is that in Chem 1B, you have to do a lot of quadratic equations, and Chem 1B is not an algebra class. And so you're allowed to use a solver, you know. And so you go here, you look at the different modes. And so if you go to, on mine, mode 5, which is equation, it has these. And so it solves up to cubic equations. And all you have to do is plug in A, B, and C for quadratics, or A, B, C, and D for cubic equations. And then you'll get your X1 and X2 for quadratics. And then, so this saves a lot of labor. Unless you like doing a lot of quadratic formulas by hand, you want a calculator that has it. Now, it's not just Casio, TI has it, a bunch of other calculators have it too. This is just the calculator I ended up getting. But I don't know if we're doing any quadratics. We might do one quadratic in this class. And so this would be just, if you're gonna buy one calculator, just buy this. I know a lot of people recommend just buy the cheapest scientific, but you're gonna be doing a lot of quadratics by hand. Do that. So if you already have a calculator, then don't worry about it. No big deal. We aren't doing, you might do one quadratic in this class, like I said, or maybe not. It depends. All right, for lab, I'd like you to get this. We're going to collect data, and we want to collect data in our lab notebook. And so this quad-ruled composition notebook with some binding, that's going to serve as our lab notebook where we're going to collect the data. And so when we get to the lab portion, you get this, whenever. It's quad-ruled. You could get college-ruled also. The quad-ruled's convenient because it's easier to draw tables and also make some crude plots in there. It has to be sewn binding. This is one of the things. They don't want the pages easily torn out. When pages are easily torn out, that doesn't really constitute a lab notebook. A lab notebook, it has to be more permanent in nature. And so it's just one of those comp books you get at the office stores, like Office Depot or Staples or wherever. Our bookstore has them too. Okay, you'll need these when you go into lab, safety goggles. We'll talk about the requirements for safety goggles. Safety goggles are a little different than safety glasses. Safety goggles are supposed to offer some splash protection and also a little side protection as well. Safety goggles are actually, there are two types of safety goggles. One for splash and impact, one strictly for impact that you get, and so we need the ones that have splash and impact protection, not just impact protection. Visor goggles fit that. This is the type of goggles that we sell. We only sell one type of goggle at our bookstore, but there are tens and tens of different goggles that you can buy. And a lot of people go to Home Depot and buy the $2 goggles, but those have a lot of ventilation holes, including on the bottom, and they don't provide adequate splash protection. Optional items here these are for lab, Sharpie for labeling, glassware. They're permanent, but you could use some alcohol that'll take it right off. Or just rubbing. Sometimes just rubbing it off with a paper towel, take it off. Lab coat and nitrile gloves. I prefer nitrile gloves over latex. Latex aren't very breathable. Nitrile are much more breathable. Also, nitrile are much more resistant to chemicals. Eventually, when you're wearing gloves, the chemicals will seep through, because it's small particles will eventually seep through. And then once they do that, then it's been saturated. It's like a sponge. Once a sponge has been saturated, it doesn't really provide much of a barrier. And so the nitrile gloves are more resistant to a wider variety of chemicals than latex gloves. And they're more breathable as well. And so they're much more comfortable. Lab coat and gloves are required now. They're not optional at UCLA and other university labs. Those are all required. All right, so let's stop here. We're going to take a break, and then this is what the homework is going to be in this class. We'll take a break, and then during this break, you should go back and look through your notes. Are you taking notes? And then you got to go back and look through your notes and make sure you wrote down everything. And if there are questions on what you wrote down, then put a little question mark or something next to it. But we'll have like a 15-minute break, so there'll be some time to go back through and look. And then when we resume, let's get things cleared up from what we were talking about earlier. All right. All right, so it's 12:35 now, so 12:45, 12:50. Let's come back. We'll come back at 12:50. How about that? Is that good?
Yeah, that's good.
Okay, thanks. So I'm going to pause the recording and did you have a chance to look back then at your notes, what we just talked about? It's not that much stuff, but was it clear? The definition of chemistry here we had talked about. The difference between properties and reactions. The difference between substance and mixtures and matter. Okay. Pure substance would have what we call a fixed composition, like water. You know, water, the composition is fixed. That is, there are 2 hydrogens for every oxygen, so that's why we call it H2O. Whereas a mixture like sugar water would have a variable composition. And so something with variable composition will have varying amounts of sugar. It could be, you know, not very sweet, or it could be extremely sweet sugar water. And so that's one distinction. Another distinction is that in a mixture versus a pure substance, since it has a fixed composition, it's also going to have fixed properties. So water we can characterize by its properties. The boiling point of water would be 100 degrees C. The freezing point would be 0. The density would be about 1 gram per milliliter or cubic centimeter. Where sugar water, you know, the boiling point varies depending on how much sugar is in the water. The more sugar there is in the water, the more it varies from 100 degrees C. That appear, and the same thing with its freezing point and its density as well. If there's a lot of sugar in the water, its density is going to vary, and its density is going to vary depending on how much sugar. And so in a pure substance, it's fixed composition. In a mixture, it's variable. And so what has fixed composition? There are 2 types of things that have fixed composition. One is the element, and the other is a compound. You know, a compound would be, an example would be water. Or a compound would be pure sugar. You know, sucrose is the sugar that we normally think of, or the like. You know, just 1 second. I got to do one thing. Just 30 seconds. Let me know if that answers the question. Be right back. Turn off the AC, it's getting too cold. Okay, great. Were there any other questions? You know, did you guys catch all of that? Since we're in class, you know, practically the whole day, I mean, 6.5 hours or something, or 5, yeah, 6.5 hours. That's going to be the homework. I don't have any, I'm not collecting any homework this semester, but the homework is going to primarily consist of going back through and you know, what I found to be the most effective way of studying is to take a complete set of notes. If you take a complete set of notes and you understand everything in the notes, and you can do all the problems that you did in the notes, then, you know, that's 90% of the class. You know, 90% would be an A. And so as long as you understand everything that was covered in lecture, you're good. And the problem is that a lot of people miss stuff that's covered. You know, typically when people take notes, like when I took notes, I'd miss a lot of stuff. The professors would usually talk very fast and they wouldn't write much stuff on the board. And so I ended up missing, because I can write very fast. And so I ended up missing a lot of stuff. Well, if you miss a lot of stuff, then all of a sudden, you know, your notes, you know, if you understood everything in your notes, maybe you got 80% of it, that's a B, or maybe 70%, that's a C. or 60%, that would be a D. So, you know, even if you have what notes you took mastered, that's only, you know, covering 60% of the material. That's not very effective way of studying. And so you want to get, you know, as close to 100% of the material as possible. You know, when I went to UCLA for my undergraduate, and I got my chemistry degree there. When I was there, they have a professional note-taking service. They probably have this at Dominguez too. But most universities, they'll have it. And that's very helpful because then you don't miss anything, you know. But normally what I did was I couldn't write fast enough. And sometimes I misunderstood things, so I didn't write. But what I did was I tried to write down as much as I could. And then right after class, you know, I might not have written it down, but I remembered, you know, something that was mentioned. And then after class, I could write it down. So like, that's why the 15-minute break, you know, during that 15-minute break, you might not have written it down, but, you know, you might remember it, and then you could write it down during the break. So when I was a student, I tried to keep the time after class free. You know, I didn't like back-to-back classes because that didn't give me time to fill in my notes, because I'm just a slow writer. And so I like that, you know, after class, like when I was a student at UCLA, after class, I'd just go to like the coffee shop or Kirkhoff or find a table, and then just try to fill in all the blanks in my notes as much as possible. That was important because, you know, if you have a 1,000-page book, you know, you don't want to be studying 1,000 pages for the final exam. It's way too much. But let's say, you know, you have that 1,000 pages condensed into, let's say, 100 pages of notes, then it's very easy. You know, studying 100 pages of notes versus 1,000 pages textbook is different world altogether, different universe altogether. And so it's important to do that. And so that's kind of your homework for this semester, is to make sure you understood everything in class. Okay. The other thing I did was, you know, this is only 6 weeks. And so we're having exam 3 and the final exam in the same week. I mean, go back here and look. And so how do you review, you know, how do you review the course in one day? You can't. It's impossible to review the course in one day. And so as a student, what I did is, this is not far off from UCLA. UCLA is on quarters, you know. On quarters, there's 10 weeks plus final, so altogether 11 weeks. And so here we have 6 weeks, including the final. And so what I did was, oftentimes, you know, this kind of scenario comes up. So what I did was I changed the way I studied. I started off at Santa Barbara City College as a geology major. I was originally a geology major, and I still like geology quite a lot, and then switched over to chemistry. But at UCLA, I kind of refined my study habits. With my notes, you know, it's easy. By the time the final comes, I had my notes memorized here. And so I had 90% of the class memorized by the final. And how did I do that? I don't have exceptional memory. I have very poor memory. And all I did was I read them. And so on day 1, I read all my notes. Well, you don't have that many pages. And day 2, I read my notes, you know, from the beginning to the end. Every day I read through my notes beginning to the end. And so by the time I get here, you know, I've read it so many times, not just once. I'll read it, you know, maybe multiple times in a day. And that's the way I memorized everything. So it's not all memorization, of course. You know, you have to be able to, you have to go beyond that. You know, there's always going to be challenge questions, but the challenge questions are so much easier if you have all the basic knowledge memorized, you know, because then you aren't, you know, struggling to remember this or that. You can just really dig into the challenge problem. So, you know, all the, like 90% is just regurgitation of the material that I found when I was a student at UCLA. 90% of the exam was easy, then 10% was hard. And that 10% was a lot easier because, one, you could spend a lot more time doing it because you aren't wasting a lot of time doing the regurgitation type problems, you know. And two, when you have all that stuff memorized, then it's easier to think of solutions to more challenging problems a heck of a lot easier. And so I recommend that. So your homework would be doing that. We're going to have a lot more material, but it's a lot better than memorizing 1,000 pages worth of textbook. Memorizing 100 pages worth of notes is a lot easier. You can't reread the textbook every day from the beginning to the end, but the notes you can. I'll have some other study tips as we go along, but here, I didn't modify this for our distance learning class. I'd like you to attend, but all these sessions should be recorded, and so I know they're long, but normally you would have to attend. We are going to have some quizzes, so it's possible you might miss a quiz, but the quiz is only 4 points, so it's not fatal if you miss a quiz. And those are going to be during, lecture and lab meetings. The exams, of course, you don't want to miss any exams because that would be much more of a bigger hit. It's more than 10% of your grade to miss one exam. Like I said, the homework is just going to be this. It's not going to be graded, but it's just going to make sure that your notes are complete and that you go through it. And we'll talk about the end of chapter problems too. We're going to be doing a whole bunch of those. Okay, the laboratory assignments, those are going to be reports and that type of stuff. Check out, you aren't going to be checking in, but we're going to go through the process. This is how you check in, this is how you check out of the lab, so that if 1A goes back to, at least they're talking, maybe in the fall, halfway through, they might go to on campus. They might not. We'll see what happens. Take the final. Yeah, makeup, there's no need for exams. The exams, we'll talk about that more as we get closer. But I think, yeah, you'll have some time for those. Okay, this is an error. Shoot, I don't know why I did that. Can you, sorry, can you cross this out? This is when this is for a different syllabus when I had more exams. I had a weekly exam for this one, and I forgot to delete that here. But if you could delete this, we aren't doing weekly exams here. And so I had a lot more exams. And so unfortunately, we're not going to drop any exams for this summer. So please cross that out. It wasn't a weekly exam, it was a chapter exam. So I had an exam every chapter, which was kind of like a long quiz, short exam. So I had 19 exams, kind of thing. Makeup labs, well, everything's being recorded. So the labs will be recorded as well. So there's no need for a makeup lab. Your lowest 15-point lab, well, shoot, how did I screw this up? I thought I fixed this, but I guess I didn't save it. I think that was the problem. I didn't save it, and then I created the PDF. Okay, excessive absences, yeah. I don't know how that's going to work for this distance edit. We won't worry about it right now. Okay, so we're going to have 3 exams, as you saw in the syllabus. Each of one will be worth 100 points. And then what I'm going to do is I'll probably post a sample test on Piazza so you can get an idea. But the exams are going to be a mix of multiple choice and like free response calculation type problems you'll do. It'll be lecture concepts and calculations like based on end of chapter type problems or whatever we discuss in class. There are going to be 12 labs, and the reports is going to be 10 points. Some of the labs are like a double lab, like experiment 12 is a double lab, experiment 10 is a double lab. So those would be, 20 points, but they're the 2 reports, one for part 1, one for part 2. It's 120 points. These quizzes, we're going to have 20 quizzes, so there's a bunch of quizzes. We're going to have the first quiz today. I'll show you the quiz shortly. There's 4 points for that. And then the final exam is going to be close to 20%. This is like 19% of your grade. So the total points is 625. And so if you're above 90% of the total, whatever 90% of 625 is, then you get an A. 80% is B, 65% C. Okay, 55 would be a D cutoff. One thing about this is, like at UCLA, they have the labs and the lectures as separate classes. So you'll have a 1-unit lab class and a 3-unit lecture class. And you could fail a lab, you could just fail 1 unit. But here, since we have it bundled together, it's 5 units of lecture and lab. We have to have this for our agreement with UCs and Cal States. That is, if you fail lab, and so the lab portion is 120 points. So if you get less than, I think well, fail would be D. If you get less than 65% of 120 points, then you can't pass this class. You end up with a D in the class regardless of how well you're doing in the rest. Because we can't separate out the lab. So if you fail a lab, you got to fail the whole course, and, not just the lab, since there's not, again, there's not 2 separate grades for that. All right, okay. Okay, so I have some questions here. Let's say, Corinne, is that correct again? Corinne?
Yes.
Okay, thanks. Are the exams going to be taken during class time on Zoom? I'm still thinking about that. The exams are going to either be taken in class, not on Zoom, but on Canvas. That's one option. The other option is the exams will be taken home, will be take-home exams. Okay. This first quiz, is it Rhea or Raya? Can you remind me again? My memory's bad. That's why I have to repeat.
Oh, Raya is fine.
Raya, or actually, can you pronounce it for me?
Raya Dejani.
Raya Dejani. Okay, Raya. Like that. The quizzes. Okay, the quizzes are going to be like posted. There'll be both Piazza and Canvas quizzes. I'll let you know. And so what we can do here is, let me just show you what the quiz is. The first quiz. The first quiz I posted on Piazza. And so let me go back to Piazza here. And let's take a look at the quiz. This is your first quiz. Here, let me clear this. And so it's just, this should be a simple quiz. It's just like, just a little bit of background information. I know I already asked you name, email, I have just some contact information, whatever you're comfortable with. Just to remind me what name you would like to be called in class. If not, you know, if it's a nickname or something. Your major, I know I have your majors written down, but I'll just have it on this form here. Your goal for this course. And so just fill in some information. So I just have some background information here. And you can give me any comments. And so this is, what section is this, 1058? Let me just check really quick. Yeah, I think this is 1058, but it's not. Oh, yeah, it is. And so section 1058 You know, are you enrolled or on the wait list? I think everybody here, nobody on the wait list made it in, unfortunately. And then your name, etc. And so you could either save this as a PDF or you can print it out. If you want to print it out and then just write it, then you're going to have to scan it in as a PDF. If you scan it in, then you can use your printer, or you could use, this is what's recommended if you want to do this with your phone. A lot of people recommend this app, which is Genius Scan. The Genius Scan app. And a lot of students use this last semester. And so it's for both. It's free. You'll just get some watermark here. But you can do, if you want to print it out and write it by hand, you can use this app to scan it. Or you can just modify it here and then save it, you know, here. Okay, once you do that, then you're going to go to Canvas here.
There's some kind of
When
what
I
you call
talk
it.
about these Taco Bells a lot, huh? Some people says it's not a lot, but I think it's a lot of money.
I'm bringing sexy back.
Okay, I'm going to have to mute, I think. Let me see.
Who the fuck?
Or just make sure you're on mute.
Turn
Otherwise,
it back up. Alrighty.
I can do this.
So Medique. Oh, the perfect backup, man. Backup dancer to the Jackson
Okay, here.
back in that day.
Okay. So then once you fill this out and scan it, then you're going to go to quizzes here. And then here, there's going to be an upload, student info upload. And then actually, I need to go to student view. Let me see. It's going to look like this to you. And you'll just upload here. There's a link here. Choose a file. And you can upload it here. PDF. Then submit it here. Okay. Let's see what we got for questions. Yeah, print it out and scan it. It would be better if you upload it onto Canvas, but if it's giving you trouble on Canvas, you can email it to me as well. Okay, Raya, it's a cam scanner. Okay, cam scanner is good. Actually, cam scanner is what I have on my phone. But a lot of people have been using Genius Scan, and Genius Scan has been recommended by the school. So that's why. But Cam Scanner is good too. They're free versions of those. So are there any questions about this? Here, it's going to be in Canvas. I'd like you to upload it here in the quizzes assignment. Here. Okay. All right, we'll just move on here. Okay, so this is quiz. When's this quiz due? Yeah, can you turn this in by tomorrow? No. And so just finish this. This will be your homework or your quiz for today. This is due tomorrow. Okay, going back to this here. If there's any special requests, let me know here. You can let me know on that sheet, the student info sheet. Any course changes, I'll post on Piazza or just announce it in class, you know. Academic honesty is mandatory, of course. Getting help here. Piazza, if you have a question, you can post it here on Piazza, and anyone's welcome to answer it. Sometimes it takes me a while to get to it. So if you see a question here that you know the answer to, just go ahead and post your answer here. Help each other out. So you can use this to get some help. Piazza. There's free tutoring from the library. This is via Zoom, except I looked at the hours. Unfortunately, the hours that they have conflict with our class. I think it's like Tuesday and Thursdays in the afternoon. I asked them to put some additional hours that didn't conflict, and so we'll see. Or I just let them know that the hours conflicted. Hopefully they'll add some hours to it. There's also the MESA program. I'm not sure if they're going to have a MESA session over the summer, but these are free and they're facilitator-led, like review study sessions, which a lot of students have found useful. Just search on El Camino for MESA and see what they're offering. Internet Owl has some resources that you could use. Owl is what's bundled with a book, so let's see here. I'm logged out already. Let's see, I can get back in. So I'll just give you a glimpse of Owl here. Okay, you go under study tools here. I don't have any homework assignments in Owl. Owl's online homework / study. And so they have the ebook here. I think yours is bundled with the ebook too. The ebook is kind of nice because it includes additional stuff, multimedia stuff beyond the print version. And so if we go to chapter 1 here, and what I did was some of this multimedia stuff, probably not all of it, but all of it so far, I just made a video recording of it and embedded it into the PowerPoint. Let's see, what can I get? Actually, I don't want to go to chapter 1. Let me show you chapter 2. Yeah, like little videos here that they have in here. All right, so that's the ebook, and I think that's available on OWL. So let's go back here. Of course, Khan Academy has videos, and there are other resources, lots of resources now. In addition, there are other textbooks. The other textbooks we have in the chem study room. We have a little study room / library in the chemistry building. And there's a bunch of old textbooks there that are helpful. Or Wikipedia. Wikipedia does often have some good useful information there as well. All right, are there any questions on the course info here? Okay, when do you want us to get the book and handbook by? Well, as soon as possible. Ideally, like now, today. But I mean, you can get by just for right now on the PowerPoints and stuff. But the sooner, whenever you can get it, as soon as possible. But if you need more time to get it, that's fine too. I mean, Some dates are wrong on the syllabus. Okay, let's take a look at the syllabus here. Screw that up.
I believe that starts from August 6th. I looked at on my phone calendar, and I think that day, August 6th, it's a Thursday, I believe.
Okay.
Yeah, so I was like revising it and putting it on my agenda, and like it's coming out as August. It's a Thursday for August 6th.
Shoot.
Yeah,
Okay.
yeah, I was
August 3rd is what I meant, huh?
okay.
Oh, gosh. All right. Thanks for catching that. I think, I don't know what I did here, but yeah, thanks. We'll fix that now. That's correct, Crystal. So can you guys do this? We might as well just correct it now here. All right, so that's going to be the 3rd, 4th, 5th, 6th, and then this would be the 10th, 11th, 12th, 13th. So 13 should be our last day, August 13. Let me check that. I guess I was on the wrong month. Yeah, 13th is our last day. I'll fix that, and then I'll post a revised version of this on Piazza. But did you notice anything else? Yes. All right. Well, like I mentioned before, I started off as a geology major at Santa Barbara City College, and then I decided to change my major, when I hit mineralogy. When I got to mineralogy, we're identifying minerals based on the color and the shape of the crystals and that kind of stuff. Whereas in chemistry, we're already using instruments, and so I liked using instruments like rather than basing it on visual tests. But it turns out geologists use instruments as well. So I didn't have to change my major. But anyway, I changed it. And then I transferred to UCLA, got my bachelor's. And then from there, I went to UCSB and so got my PhD in chemistry, inorganic chemistry. I looked at chemistry of materials, primarily optical materials, things that pass, like infrared light. In fact, I was looking at infrared optical materials, things that acted as infrared transmission lines, like fiber optic cables, that kind of stuff. So, and as well as other things, I looked at a bunch of different types of materials, mostly what we call inorganic, non-biological, inorganic type things. But anyway, it's all kind of the same set of rules, whether you're a biochemist, a geochemist, a physical chemist, everything behaves by the same set of rules. So the same rules apply to biochemistry as it applies to physical chemistry. And so it's not difficult to jump from one field of specialization to another in chemistry. We're going to be looking at the rules in this class for chemistry. All right, so we have a lot of stuff to cover, and I want to just get into it right now. And so if you go to Piazza here, I did some PowerPoints here. And so this is Chapter 1 PowerPoint here, which I already have open. Chapter 1, actually I don't have open. Do it here. And so I can download those. Open it. And this is slow. All right, I got it open here. All right, Chem 4, summer, it's me. So chapter 1, there's not that much stuff to cover, but let me make sure I'm recording here. Yeah. So let's talk about science. You know, what is science? What do scientists do? You know, when you think about what is science, like somebody asks you, you know, what is science? And follows up with a question, what do scientists do? And then more specifically, what do chemists do? You know, what would you tell them? This is not coming from this doesn't have to come from the dictionary, but this is what I'd say. You know, when I think about science, what is science? You know, science is, you know, science just describes. Actually, let's go with a different color here. Probably red's not the best color for this. When I think about science, I think, you know, science just describes nature, you know, describes nature. But they do it in a much more quantitative way. Quantitative is like with hard numbers and measurements and this kind of stuff versus qualitative, you know. Qualitative would be just rough approximations, like, you know, that's a pretty shade of blue, let's say, versus quantitative, well, that blue has a wavelength of this and this number of nanometers, you know. And so a scientist was going to describe in detail nature, you know, and so describes nature. And we want to describe nature so that we can understand it, you know. That's what it is. And so what scientists do is they just, well, scientists try to describe nature. That's what they do. Nature being, you know, the world around them. And so scientists just describe nature. And so maybe you say describes nature in detail, you know, and you know, trying to be, you know, quantitative. Trying to be as quantitative as possible. Say being as quantitative as possible. That's what I try to do. Versus qualitative. These are two words that are often used. You know, qualitative would be that's a lot of stuff. You know, that person has a lot of sugar in their coffee. Versus quantitative is that person put, you know, 3 sugar cubes, or maybe that person put 3 grams of sugar in their coffee. and how much coffee, 200 milliliters or a cup of coffee or so. And so scientists are working at describing nature in detail here. And chemists, chemists are going to describe what was that? Describe what would you say? Do you remember? Describe can you tell me? Does it come right off? Well, by the end of the semester, it should come right off, off the tip of your tongue. Yeah, that's one of them. When he said, what were the other two? Well, if you say chemical properties, and there are three more. What were the other three? Yeah, but I'm looking for, it matters at the end. Describe the blank, blank, and blank of matter. So matter is going to come at the end. What is the blank, 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 or blank, 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 blank? Yeah, composition, right, you got it. Composition, structure, and properties. When I say properties, what do I mean? Composition, structure, and properties. When I say properties, I mean both physical and chemical. Yeah, that's correct. And so properties here, this is why my definition only had 3, whereas the Houghton Mifflin had 4 because they separated it. But for me, we incorporate both the physical. If you can't read my writing, let me know, because sometimes I can't even read my writing. So let me fan up the pen here. So we have physical and chemical. Give me an example of a physical property. Give me just one example. Point? Melting point? Yeah, that's a good one. Melting point. Shape is another one. How about any others? Melting point, shape, color is a good one. It's good. What do you say taste? Is taste, let's say it's an edible chemical. Would taste and smell, would that be a chemical property or would that be a physical property? Usually, yeah, that's tricky. That one's pretty tricky because you might think chemical because there's going to be some kind of reaction with their taste receptors, but that reaction turns out to be more of a physical reaction than a chemical reaction. And so it turns out like taste and smell are more physical based on the receptors, and so those would be physical. We have, when we're talking about physical properties, there are 2 types of physical properties. Did you know that? Does anybody know the 2 types of physical properties that we encounter? One type of physical property is intensive. Another type of physical property is extensive. So does somebody know the difference between an intensive physical property and an extensive physical property? Or at least can give me an example of one of each? Maybe you could figure it out based on the categories here. So for example, in intensive, color is borderline. It could be intensive or extensive. It's borderline. But there are some things that aren't necessarily borderline as far as intensive goes. Let's go to extensive. Extensive, let's do that. For example, an extensive property would be mass. Let's just do mass would be an extensive property. What else might be extensive? Well, mass is a pretty good one. As far as intensive properties go, melting point would be a good example of an intensive property. Now, what's the difference between these two? Can you see it already? Melting point versus mass. Actually, where does density fall? Density is kind of related to mass, because if something's quite dense, it's pretty, usually weighs a lot. Something's quite dense. If something's not very dense, it doesn't weigh much. So density, does density fall in the intensive category or the extensive category? What would you put it in? Extensive, Carlos? Extensive, Moniz? Extensive. Yeah, okay. Anybody for intensive? We got nobody for intensive. Yet? No? Last call for intensive? All right. Well, melting point here is an intensive. Boiling point, density. Density is intensive, whereas mass is extensive. So what's the difference there? The difference goes like this, which weighs more? You probably heard this before. Which weighs more, a pound of feathers or a pound of gold? Which one weighs more? A pound of feathers or a pound of gold? Yeah, they're both the same. You're right. They're the same. And so a pound of feathers weighs the exact same amount as a pound of gold. But what's the difference? Is there any difference then? Well, yeah, gold is much more dense. The quantity, the amount, exactly. A pound of feathers, you'd need a lot of feathers for. A pound of gold, you wouldn't need nearly as much. And so the difference between intensive means independent of amount. Intensive, independent of amount. So let's say you're going to melt some ice. The melting point is the temperature at which it melts. And so if you warm up the ice to 0 degrees C, it starts to melt. So if you want to maintain the ice, keep it below 0 degrees Celsius. Does it matter though? Like for example, if you're melting a pound of ice versus 2 pounds of ice, does the melting point change for 2 pounds of ice? In other words, does 2 pounds of ice have a different melting point than 1 pound of ice? And it turns out they have the exact same melting point, And so it doesn't matter how much you have. Like the density of gold, the density of gold doesn't change. Gold is very dense. Gold is one of the most dense, If you look at gold has a density of above 19 grams. Gold is approximately 20 grams per milliliter or cubic centimeter. So cubic centimeter is cm cubed. Versus water. Water has a density of around 1 gram per cubic centimeter. And so gold is 20 times more dense than water. So if I had a cubic centimeter or cc, gold would weigh 20 times that. Lead, what do you think is more dense, gold or lead? Which one do you think weighs more? If I had a cubic centimeter of all of them, which one would weigh the most? A cubic centimeter of lead or a cubic centimeter of gold or a cubic? It turns out no, lead is about 13. Do you guys know the symbol for lead? Yeah, this comes from plumbium. This I think is Latin as well for lead. Plumbium, PB. That's about 13 and a half. Let's just say about 14 grams per cubic centimeter. These are qualitative. If I wanted to get quantitative, then I would try to pinpoint it more, 13.5, 19 point something for gold, I forgot. 0.999 for water. That would be becoming more quantitative. We try to be as quantitative as possible. The densities we can find, if you want the densities, those are, and you can get reliable densities off of Wikipedia. I know a lot of people say Wikipedia is not reliable, but for a lot of the scientific information, Wikipedia is pretty reliable. I mean, just for properties, Wikipedia is going to list the properties of things like gold and lead. Let me leave this up here. I know it's a mess, but let's search for gold. I wonder if it'll recognize the symbol for gold. AU, Australia, that makes sense. So the properties, the physical properties are going to come here. And so we're going to have some physical properties. Like, for example, the melting point of gold is 1064 degrees C. You know, for ice, it's 0 degrees C. So gold has a very high melting point. Boiling point, well, once you melt it, you're going to get liquid gold. And if you try to boil liquid gold, you're going to have a tough time because that's almost at 3000 degrees C. If you look at the density, now the density changes with temperature. So this is near room temperature. Room temperature is taken as 25 degrees C, which is a little warm. It's like 77 Fahrenheit. So, but the density of gold is 19.3 grams per cubic centimeter. Yeah. The liquid gold is a little less dense at 17, but this is very high. This number is very large. Although it's not the most dense, what we call element. There's elements that are more dense than gold, like iridium, osmium. Those are the two highest densities, I think. There's some other properties here. These are all intensive properties, physical properties here. These physical. Extensive, it wouldn't make much sense, 1 pound of gold, 2 pounds of gold. That doesn't make much sense. Color is very tricky though, because color sometimes depends on the amounts, the color to the naked eye. But if we look at what we call the spectrum of gold, if we look at the spectrum, then that doesn't change, This is the spectrum here. It is possible that the spectrum changes a little bit depending if we have nanoclusters. With nanoclusters, we might see little differences in that. And so color can be tricky to our eye because our eye can be perceive colors differently. So that one's a little less concrete. So density goes here. Color, like I said before, depends on how you measure it. If you're looking at with your eye, then it depends on the amount. This is why in geology, when you look at the crystals, like, have you ever looked at salt crystals? What color are salt crystals? Like tables. Let's say you put some salt on French fries. What color is that salt you put on the French fries? White, right? But have you ever looked at one single salt crystal? When you look at, I don't know if you've done this, but take a look at one single salt crystal and tell me what the color is. It's clear, it's colorless. There's no color. And so there it depends on the size of the crystals. It's totally transparent, you're right. And so what geologists do is do a scratch test. What they do is they just get a porcelain plate and they scratch the mineral on the plate. When they scratch the minerals, it creates tiny crystals, and those tiny crystals give you a consistent, if you do a scratch test for all of them, you get a consistent crystal size, because depending on the crystal size, it changes the color a little bit to your eyes. And so we need a consistent crystal size. So that's called the scratch test in geology. And that was one of the things that we did in mineralogy to figure out what the color is. And so you want to make a fair comparison. All right, now chemical properties, we don't have intensive and extensive, but what kinds of chemical properties are there? And so when we think about chemical properties, so we'll just leave the physical properties at that for right now. But extensive mass, volume, What else would be extensive? What else depends on the amount? There are others, but I can't think of them. Chemical, we're looking at reactions, as we said before, chemical reactions. And so what types of reactions do we look for? Well, we look, is it flammable? You know, can you burn it? So flammability or combustion, you know, that's an important one. And others, there are others. And so there are different subtypes of chemical reactions that we look at, which we're going to talk about in this semester. All right, so what we want to do is we want to just understand matter, the matter and interactions of matter. And so of matter, and I'm going to add that, of matter and its interactions with, let's say, empty space, a vacuum, or interactions with light and its interactions. Okay. And so that's what chemists do. We're very interested in composition, structure, and properties. These are related. In fact, when chemists think about the composition, structure, and properties, you know, these are all interrelated. The composition for sure is going to have, you know, impact on how it behaves, like the composition of the air. You know, is it polluted or is it relatively free of pollutants, you know, contaminants, that kind of stuff. You know, how much oxygen's in the air. You know, as you go up in higher and higher elevation, you know, air gets thin there. Air gets thin. There are different ways of representing the composition, you know. But there are certain things like, do you know what diamonds are made out of? Yeah, coal. What's coal made out of? Carbon. Yeah, diamonds are made out of carbon. Coal's made out of carbon. And so what's the difference between diamonds and coal? The only difference is the structure. That's the difference. Properties. Maybe I should have properties at the top. Doesn't really matter. I could rotate this, whatever, you know. But these are all interrelated, you know. And so we try to understand chemistry in terms of composition, structure, and properties. You know, we're very interested in how things behave, you know, how things behave are the properties. And in order to understand that better, we need to understand what it's made out of and how it's structured. So for example, graphite and diamond are both made out of 100% pure carbon. Those are pure substances, but their properties are quite different. And the properties are quite different because of how the carbon, you know, the carbon atoms, the small pieces of carbon are arranged in those two things. Okay, let me clear this. Okay, so chemists, you know, when we're talking about chemistry, what do chemists do? Chemists describe nature. That's what chemists do. You know what chemists are good at? What scientists do? Let me just add this. You know what scientists do? Scientists do this. If you want to just come up with a simple statement, scientists observe nature. They observe nature. If you want to describe nature, you got to take observations, and you want to take quantitative observations, you know, and trying to describe nature as quantitative as possible. That's what we do. Now, okay, sorry. However, in the past, that hasn't always been the case. You know, in the past, there was some magic to chemistry, you know, and that magic was a magical component to chemistry. It's not really science, you know, the magical component. You know, chemist is just, it's in a way, science is a little boring because you're just describing nature. You know, You know, you're not making these magical predictions. These magical predictions have been made in the past in alchemy. Alchemy was what preceded chemistry. Chemistry is more of scientific based. Alchemy had a mix of science and magic to it. And so what was the magical part of the alchemy? Well, there are two things that alchemists were seeking. You know, one was the philosopher's stone. Have you ever heard of the philosopher's stone? And what the philosopher's stone is capable of doing? Yeah, maybe. I don't know if that was supposed to be the answer, but we'll take it. I'll take it. Any answer at this point. Any others? No? All right. So that's good. You haven't heard of the philosopher's stone. You probably haven't heard of the philosopher's stone because it's no longer relevant. You know, it's a great thing. Everybody would love the philosopher's stone because you know what philosopher's stone would do? Yeah, it turns stuff into gold. Who wouldn't want that? You know? So Carlos, would you dedicate your life to seeking the philosopher's stone in today's? Yeah. But, you know, I think everybody would, but what is the likelihood of finding it? Like this person, you know, this person looks like he's dedicated his life to seeking the philosopher's stone, but did he ever find it? No, actually, no, because nature doesn't work like that. We know nature doesn't work like that. And so this philosopher's stone, you don't hear about it anymore because it's just not how nature works. And what we do is we observe nature and see how things work. And so this is a kind of a magical component. It would be fantastic to have the philosopher's stone because the philosopher's stone converts like base metals into gold. And so you could just take any metal and convert it into gold. And the science part of that is they saw that you could form alloys, you know, you mix metals and you get a different metal. And so they kind of made sense, you know, but based on real observations of how nature works, it just doesn't work like that. You just aren't going to get gold. And so that's one thing. How about the elixir of life? Have you heard of the elixir of life? You know, everybody would want this too. I think almost everybody would want this. The elixir of life. Okay, maybe on video games. Well, what does elixir of life do? Immortality, right? And so are you going to dedicate your scientific career and invest all your money into deriving the elixir of life? No, because this is not science here. And this is not what scientists do. You know, this is what the alchemists do. They did a mix of science and reality, but this isn't. So what do scientists actually do? And so after this is around the time, 1771, 1624, around this time is when science really matured into it. Here, this is kind of low resolution. This is from the book. Antoine Lavoisier. Lavoisier was credited with scientific rigor. You know, in fact, this book here is the first real chemistry textbook. This was published in 1789, so almost the 1800s here, and some this time. And so Lavoisier was doing science as science is done today, and science is just a description of nature. So hopefully you guys are still going to make it. You got to think. You got to think about this class. This is kind of brutal class as far as time goes. And oops. And so I'm sure a lot of people are in disbelief. I mean, it's this many hours, including me. It's a lot of hours. lot of hours to be here, but make sure you're okay. But going back to this, so how did Lavoisier approach it? Well, preceding Lavoisier, people knew one of the chemical properties. Can you tell me one chemical property that burning wood? Yeah, burning wood would be one chemical property. Let me do something really quick here. Okay. Yeah. So burning wood is one. So when the early alchemists were looking at wood, and so this comes from alchemy, phlogiston. Let me just go back to annotate this. So the alchemists proposed there's some mysterious stuff called phlogiston. You know, I don't know if you call it a substance, because substance would have to have matter and occupy space. In other words, it would have to have mass and occupy space. So phlogiston didn't necessarily have. But what they noticed is when they burned the wood, you know, so when you combust wood, and so we'll have this little arrow. This arrow is representing this chemical transformation or chemical reaction that occurs. And so we start off with wood, we end up with ash. And the amount of ash that we end up with is minimal, you know, compared to the weight. So what happened to, when we look at the mass initial, okay, mass initial versus the mass final, we see that there's tremendous difference here. And so what must have mysteriously, magically gone away is this phlogiston stuff, phlogiston. And so what they said was anything that combusts possessed phlogiston. And so wood possessed phlogiston. And anything else they could burn possesses phlogiston. But Lavoisier, he was skeptical of that. That's science is pretty, scientists, modern day scientists are pretty skeptical of things, so they want to test it. And so one of the things that Lavoisier did was he burnt phosphorus, the element phosphorus. He burnt it in a balloon like this. Yeah. And what he found was that the mass initial was actually smaller than the mass final. So this is white phosphorus. And the symbol for phosphorus is P. And so this is P. White phosphorus has this symbol. It's P sub 4. That's white phosphorus. And so you burn this, and then the mass initial, here, the mass initial was greater than the mass final. Here it was the opposite. The mass initial was less than the mass final. And so this one gained mass or gained weight. This one lost weight here. And so we end up with this powder. This is white solid that we end up with. This white solid is not phosphorus. How do you know it's not phosphorus? Well, because phosphorus would have certain physical characteristics, which we call properties, that this white solid did not have. You know, this white solid behaved a lot differently than the original stuff, so the properties were different. And so it's not phosphorus based on properties. It could still be a pure substance. Maybe we ended up with a pure substance here, but this is a new substance here formed. In fact, it was in this case. Another thing that happened is the air. If you look at the air volume went down here. And so if this phlogiston, why wasn't it losing? When it burned, it should be losing the phlogiston and becoming smaller. And so this is an experiment that that debunked one of the parts of the phlogiston, this phlogiston theory or hypothesis, whatever you want to call it. Okay. Let's continue on here and delete this. Joins. Move on. What is phlogiston? No, nobody knows what phlogiston is. Just a mysterious stuff that combustible things possess that disappears upon combustion. And so that was the magical kind of thing about it, you know. Something was lost and they didn't know what was lost, so they just called it phlogiston. This stuff. Well, let's talk about phosphorus. So you know, I called it white phosphorus. Phosphorus, these are all 100% pure phosphorus. These are pure substances here, although this one doesn't look so pure because there's some white stuff here. So this one, the rest look pure. They look pure because they're fairly homogeneous in color. So if I look at this looks pretty homogeneous. And this is actually, even though it looks kind of yellow, this is called what we call white phosphorus, and it's waxy. It's really waxy. This is red phosphorus. Red phosphorus, which is also 100% phosphorus, these matches. And then we have black phosphorus over here and violet or purple phosphorus here. And these are all 100% phosphorus. So what's the difference? Well, their properties are certainly different. You know, look at the colors are different. And also their feeling, like this is a waxy solid, this is a powdery solid here. This is brittle solid here. Some of these can have the rubbery texture to them and other things. So when we look at it, yeah, the properties are different, but their compositions, oops, stop there. But what accounts for the differences in properties? Well, what accounts for the differences in properties is not the composition, because the composition is the same for all four of these. What's accounting for is it must be the way it's structured. You know, how are the, you know, phosphorus, when we think about phosphorus, the smallest piece of phosphorus that you can have is called the phosphorus atom. And so if we think about there's different ways of spelling phosphorus. There's a European spelling and a US spelling. And so I guess I did maybe the European, but let's try that again here. The smallest piece of phosphorus you can have is a spherical little, you know, called the phosphorus atom. So this would be the phosphorus atom. So it's not the atom itself that's different, you know, it's how the atoms are linked together. So for example, in P4, you have 4 phosphorus atoms linked together to form what we call a cage, like this. So this would be white phosphorus. The white phosphorus. Red phosphorus has the atoms linked together in these chains. And so it has a different structure. The phosphorus atoms are the same though. The phosphorus atoms here in white phosphorus and the phosphorus atoms here in red phosphorus are the same. The difference is how they're linked together. And the same thing with purple or violet and black phosphorus as well. Turns out white phosphorus isn't the most stable form of phosphorus. You know, here stability depends on the temperature and the pressure. You know, the high pressure is black phosphorus, seems to be preferred, and at higher temperatures, violet phosphorus seems to be preferred. At lower temperatures and lower pressures, looks like white phosphorus. The most common one that we see is red phosphorus. You know, even though it's formed at over 280 Celsius, very carefully. You have to be very careful with white phosphorus because this is not at 280. This is just a gently warmed. White phosphorus is usually stored underwater. And it's stored underwater because it doesn't like air. It reacts, well, it loves air actually. I shouldn't say it doesn't like, it loves air. It loves oxygen in air. It loves to burn. And so if you want white phosphorus to live for very long, keep air away from it. And so they keep it underwater. Air contains oxygen, about 20% oxygen, right? Is what air. If I wanted to be a little bit more precise, a little bit more quantitative, it's more like 21% oxygen in air, you know, but easy numbers to remember would be like a 20-80, 20% oxygen, 80% nitrogen in air. Oxygen is what we call an oxidizer. You know, oxygen likes, like if you have a fire, you know, you need some oxygen, which is the oxidizer to get it to burn properly. And so nitrogen, though, nitrogen is fairly stable. You know, when you inhale nitrogen, it's unreactive. Chemically, you know, the chemical properties of nitrogen aren't very extensive because nitrogen doesn't react with much. You know, it's pretty stable stuff, the nitrogen. It does react with some things, but not so much. So the chemical properties of nitrogen are not very extensive. But oxygen, the chemical properties are more extensive, oxygen. And so what happens is when you expose the phosphorus to air, it'll start to burn. So let's see this video here. Let me go back to the beginning. And so, okay, this is supposed to be white phosphorus, but you can see, do you see it's discolored here? That's due to contamination. That is, it's undergone some oxidation or undergone some changes here. So it looks kind of heterogeneous, you know, white and red here or something, although that's probably not red phosphorus. This looks like some surface reactions were taking place here. And this is water. Some things are stored underwater, you know, but water can be a reactive species as well. So sometimes it's stored under oil, you know, to protect it. A lot of metals, they'll put an oil coating on there. And they'll put an oil coating on there to protect it from air, you know, oxidation. So let's watch this video here.
Phosphorus is stored underwater. A small piece is removed and placed on a warm reaction plate. It reacts vigorously, giving off a white smoke.
All right, so that's a chemical property of phosphorus here. You know, phosphorus, we call this pyrophoric. Pyrophoric is you don't need a spark to ignite it. You know, this had just to warm up a little bit, and then it immediately started to combust. At room temperature, it would start to combust as well, but just not as fast as that. And so it's pyrophoric. Pyrophoric materials, you don't need a match to ignite it. It'll just ignite by itself spontaneously. So this is a chemical property. We could say of phosphorus. Red phosphorus, you need a little bit more, you know, to get that to ignite than white phosphorus. You know, white phosphorus is a little less stable than red phosphorus. Here, it's more stable, more difficult to ignite. Here's
I
another.
have a question. Sorry.
Okay, go
Can
ahead.
you say it again? It was pyro. How do you spell it?
Oh, okay.
Sorry about that.
So one of the chemical properties of white phosphorus is it's pyrophoric. P-Y-R-O-P-H-O-R-I-C, pyrophoric. Red phosphorus is not pyrophoric, nor are these. These require, all these are combustible, but these would require a bit more work to get them to combust, like this. Or it's a little bit more work to get it to combust. But all these are flammable, are combustible, and so that's a chemical property. They're all subject. When we're talking about, you know, something being flammable, we usually need some kind of oxidizer, like oxygen, to oxidize it. And so that type of chemical property is called a redox, oxidation reduction type reaction, which we're going to talk about this week as well. Okay, clear those drawings here. Here's another experiment that Lavoisier did. He put some mercury in here and then oxidized the mercury. I don't think this made a flame, but like the phosphorus, but it's still another oxidation type reaction where it reacts with the air and the oxygen in air. So put some liquid mercury in here, heated it in the furnace so that it trapped in the air, so that it burned in the air trapped in this jar. So I guess it did burn. So the mercury was vaporized. You know, a vaporization, is that a physical property or a chemical property? If you vaporize some mercury, that is, you know, evaporate. Like if water, if you vaporize or evaporate water, is that a physical or chemical property? Okay, so let me say, if we boiled the mercury, let's say you boiled the water. If we boiled the water, would you consider that chemical or physical? Okay, it turns out that vaporization and boiling are physical properties. The reason is it doesn't change. Like here in the liquid state, there's mercury atoms, because mercury consists of, you know, these spherical atoms.
Mercury 2 oxide breaks down.
Sorry. And in the gaseous state, it'd be, so those are all physical, example of physical, right? And so here they vaporize the mercury, so the mercury vapor went over here and shot up over here where it reacted with the air trapped in the jar. Well, the nitrogen in the air is very unreactive, you know, chemically it's very stable. The oxygen is much more reactive, so the oxygen attacked the mercury and made something called mercury 2 oxide. Mercury 2 oxide is this orange looking stuff here. And so that's why you see this orange solid here. Mercury metals, liquid, silver, metallic looking liquid, and oxygen's colorless. You can't see oxygen, nor can you see nitrogen, it's colorless. But the mercury 2 oxide that formed, or mercuric oxide is another name for it, is here. Mercuric oxide has a chemical property itself. Mercuric oxide is what we call a compound, and this would be a pure substance as well. It has a fixed composition. The fixed composition of mercuric oxide has one mercury. Now, do you know the symbol for mercury? Let's see, the symbol for phosphorus is P, for gold is AU. Cu is copper. Copper, Cu. Hg. You know, I don't know what Hg comes from. You don't have to know everything. But it's, I don't know, Latin or Greek or something. Hg, it's mercury. And then oxygen, it consists, mercury 2 oxide consists of one atom of mercury and one atom of oxygen. And so HgO is the way we represent it. This is HgO here. HgO solid. It's a solid. It's an orange looking solid like this. And there aren't big crystals. It looks like they're tiny crystals here. But one of the chemical properties of HgO is it's not that stable when heated. When heated, HgO can revert back to liquid mercury and oxygen. In other words, that's a decomposition. So this is what we call a two-way. And so this arrow represents, the forward arrow represents HgO going to Hg liquid and oxygen. Oxygen, do you know the formula for oxygen? You might have seen it. Or what's the symbol for oxygen? The symbol's O, but when you breathe oxygen in air, do we call it O or do we call it O2? We call it O2. O2. O2 is correct. And so this would be what we call a chemical reaction for this over here. Except, you know, what we end up with is I had one atom of O over here. Now I have two atoms of O because that's what this 2 represents. The 2 represents there's 2 atoms of oxygen that are bonded together like this. And so that's an O2. We call it a molecule. And so I have to have half. half of that. We'll talk about what 1/2 means, or I just double everything. The other alternative is I can just double everything so that I don't end up with, this S means solid. And so that's what that S means, it's a solid. So mercury 2 oxide is a solid, whereas L means liquid. So Hg has an L next to it because it's liquid. And then O2, I need 2 Hg's here. And then O2 is what we call a gas. And so it's got a G here. And so this is what we call a chemical equation for this. Let me clean it up a little bit. What is the subscript of Hg? Okay, let me clean that up a little bit. That subscript is an L. So I wrote a cursive L here with parentheses around it. And so that just represents liquid. Solid, S, liquid, L, gas, G. Those are the states. So let's see what happens when we heat it. When we heat it, we usually put a little symbol here. Actually, this reaction goes both ways. And so that's why I drew the double arrow here. The double arrow shows, one arrow shows it pointing forward from liquid mercury and oxygen. The reverse arrow shows liquid mercury and oxygen reacting, which was here. In the first step, we had it reacting to form HCO. In the second step here, we're going to decompose it. This is called a decomposition reaction. And so let's watch this reaction here.
Mercury 2 oxide breaks down or decomposes readily when heated. If we were to weigh the compound before heating and compare its mass to that of the mercury remaining after the reaction, it would seem that decomposition causes a change in the system's mass. The product mercury would weigh less than the reactant. In reality, the decomposition liberates the reactant's oxygen atoms as gaseous dioxygen O2. All matter present before the reaction still exists after it. The reaction obeys the law of conservation of matter.
We'll talk about the law of conservation of matter coming up, but this had
Mercury
some
2
stuff
oxide breaks
in
down
here.
or decomposes readily when heated.
So this is decomposition, which is decomposing the mercury back into the elements here. This change, is it a physical change or a chemical change? Now, when I asked about vaporization, you know, like vaporization of water, oops, go back to this. That is a physical change. Now, we could represent physical changes using chemical equations like this. So if I do vaporization of water, I start off with water, which is 2 hydrogens and an oxygen, and it's liquid. And then when I heat it up, I boil it or vaporize it. And when I vaporize it, I go from liquid to gas. Now, this is a physical change here. This is a physical change because steam, the gaseous water, is still water, it's still H2O. However, this is a chemical change here because what I start with is not what I end up with. I end up with something totally different here. And so in a chemical change, the chemical identity of the substances changes. And so in a physical change, the chemical identity of the substance remains the same. You know, this is state, this is what we call state, liquid state, gaseous state. It's state changed here, but it's still the same stuff here. Here, this is a different stuff entirely. There's one more thing I might as well talk about since we're on this video here. How many mercuries and how many oxygens did I have here? I had 1 mercury, 1 oxygen here. And here I had 2 mercuries and 2 oxygens.
Mercury 2 oxide breaks down or decomposes readily when heated. If we were to weigh the compound before heating.
This is a Bunsen burner here. Now the flame is very interesting. The hottest part of the flame is, this is what we call the inner cone here. This is the outer cone here. The hottest part of the flame is at the very top of the inner cone here. This can be very hot. This approaches like 1,000 degrees Celsius. And so this has to be decomposing below 1,000 degrees. If it's decomposing above 1,000 degrees Celsius, we need a hotter flame. And you can get a hotter flame by using different gases, you know, combusting, like acetylene or something else. But this is more like 800 degrees Celsius. It's quite a bit below 1,000 degrees Celsius, the flame.
And compare its mass to that of the mercury remaining after the reaction, it would seem that decomposition causes a change in the system's mass. The product mercury would weigh less than the reactant. In reality, the decomposition liberates the reactant's oxygen atoms as gaseous dioxygen.
Okay, so here, this is what we call a crystal. You know, when we look at this solid is actually consists of, and when we look at a tiny crystal, like a salt crystal or something like that, there are a whole bunch of these atoms in here. These red ones are the mercuries, the blue ones are the oxygens here. And so this would be a tiny, tiny crystal of mercury. We can't see the atoms. You know, when you look at it with your naked eye, you can't see these. You need something very powerful to see this, like a scanning tunneling microscope. Then you can see the atoms, you know, with a scanning electron microscope. Then you can see the atoms, you know, with something extremely powerful like that. But this would be a tiny crystal of mercury 2 oxide. And when it decomposes like this.
In reality, the decomposition liberates the reactant's oxygen atoms as gaseous dioxygen, O2.
Yeah, the oxygens like to pair up like this. They just like pairing up. They don't like to be alone, you know, and so this is why it's O2, not O, because they like to, and when they pair up like this, it forms what we call a molecule. This is a molecule of oxygen. We don't call this a compound. A compound would have to have 2 different elements, like mercury 2 oxide, this is a compound here. But the mercury that forms is an element. Now, the mercury that forms isn't, this is liquid mercury. In liquid mercury, these don't form clusters or pairs, you know, like this. These form individual mercuries that are free to move around, you know. And not necessarily, but oxygen doesn't like to be alone. Oxygen likes to pair like this, so that's why we get the O2 here. In this sense, it would be like, this would be the mysterious phlogiston stuff, you know, that the alchemists were thinking that was released, you know, when this reacted, but we know it's not phlogiston. In this case, it's oxygen. It's being released.
All matter present before the reaction still exists after it. The reaction obeys the law of conservation of matter.
We'll talk about that.
Mercury 2
Oops, we'll talk about that next. What Lavoisier did was he actually weighed these things. And so that was one thing. Before Lavoisier, it's more qualitative, you know. With Lavoisier, he took more rigorous measurements here. He measured volumes like this, and he measured weights or masses more properly. And he looked at the mass. So if you weigh this whole thing before and you weigh this whole thing after, the mass didn't change. If you weigh the whole thing before and you weigh the whole thing after, the mass didn't change. And you keep doing this and you see a pattern, and this pattern repeats itself. And if you have a repeating pattern like this, then we call it a law. And so that's what they mentioned here, the law of conservation of matter.
Mercury 2
Oops, I don't want to watch that again. I want to move to the next slide.
Mercury 2
Let me move to the next slide. Here we go. All right, so this is what Lavoisier is credited with. Lavoisier is credited with really starting really transitioning from alchemy, which contained, you know, part magic, part science, to pure science. You know, Lavoisier is pure science, and pure science is just using the scientific method here. So using the scientific method, this is what Lavoisier is. This kind of the breakdown of what he did. Observing a wooden log loses weight when it burns. Proposing a hypothesis. A hypothesis is a tentative explanation or tentative description, you know, of the observations. And it's a detailed description, you know, as detailed as possible. The initial hypothesis posed by the alchemists before Lavoisier, or the scientists, and whatever you want to call them, was that wood and everything else that burns contains phlogiston. When something burns, it loses this phlogiston, which is, you know, what is it? nobody really knew at that particular time. 3, he was skeptical of phlogiston hypothesis because metals gained weight when strongly heated like mercury. If this process was similar to burning wood, why was phlogiston not lost? So there was a contradiction. If you have a hypothesis and your observations contradict your hypothesis, then what's wrong? Your observations or your hypothesis? Well, it could be the observations were wrong, but if people repeat it and get consistent observations that are easily reproducible, then it's probably your hypothesis that's wrong. Predicting an outcome that should result if the hypothesis is true. Okay, so when phosphorus burns, it should lose weight. Well, that's what the prediction was. And then testing it, when Lavoisier burned the phosphorus, it gained weight. And so it was contradictory. So it failed that test. And so the hypothesis had to change. Lavoisier proposed that burning combines the substances burned and oxygen from air. How did Lavoisier know about oxygen? I don't know. You could read that. We don't necessarily have to care about it. But the scientists back then knew about oxygen and nitrogen. Testing the revised or new hypothesis and predicting. Okay, so Lavoisier tested it with oxygen and mercury in this case, and then did some additional experiments. So long story short, this is more of the scientific method that they're using. Okay, when a hypothesis is tested and confirmed by many experiments under varying conditions without contradiction, it becomes a theory. Okay. And so this, we can put the scientific method in kind of a nutshell. You don't have to know this in detail, what he did, but you should know this. And so what are the steps? So this typical steps, this is typically the way that scientists work. And the way that scientists work is this. You know, what do scientists do? Scientists observe nature. And so we take lots of observations, and we want to take quantitative observations. You know, the more quantitative observations, the better. And so you take lots of observations, and then you start to look for patterns or trends, you know. And so nature behaves in certain ways, and we see these in terms of patterns and trends. If those patterns and trends are reproducible and consistent, we end up with a law. Now, laws, what are laws? When we think about law, you know, the simplest way to do it, it's a pattern. And the most concise definition of a pattern is a highly consistent pattern. And so an example for Lavoisier would be doing lots of different chemical reactions. If you do lots of different chemical reactions in which there's a chemical change, what you see is that the delta mass is 0. Delta mass is the mass final minus the mass initial. And so there was no change in mass. Delta mass is 0. And so the most concise definition of this pattern is a mathematical equation. And so the mathematical equation would be delta M is equal to 0. That's it. And so the highly consistent pattern that we see with Lavoisier would be that, that we have this. This would be the law of conservation of mass, law of conservation of mass. What conservation means is that it's neither lost or added to. And so there's no change in mass. The mass is conserved. We neither lose it or create mass. And so that's what we end up with, the law of conservation of mass, which has this formula. This is what we call an empirical equation here. Empirical equation. And this is what we call an empirical law. Empirical just means this. Empirical means based on observation. And so empirical law based on observation. And so this mathematical equation it didn't come from any kind of theory. It just came from the observations that Lavoisier did on the many chemical reactions that he did. Now, a law versus a rule. A rule is a less consistent pattern. Less consistent pattern with lots of exceptions, or less consistent pattern with exceptions. And so law, you don't expect exceptions or minimal, exceptions. With rules, it's less consistent. You can have a lot of exceptions. It's okay. So law. But the law doesn't explain it. Why is mass conserved? Well, we have to come up with some kind of hypothesis, Lavoisier came up with this hypothesis that it's reacting with oxygen, but in Lavoisier's time, atoms weren't necessarily, this video skipped about a century's worth of science, a couple of centuries, going from Lavoisier. And so that video is already talking about atoms and everything else. And so why is mass conserved? Well, let me just tell you this. Do you believe in atoms? Have you ever seen an atom? And what does the O with the line? Oh, that just means zero. Zero. Delta M equals 0, yeah. Do you believe in atoms? Okay, prove it to me. Give me some proof that atoms exist. Yeah, do you believe in atoms? In atoms. Let's say, to be a proper scientist, you should be skeptical. So I'm skeptical of this whole idea of atoms. I don't believe atoms. I've never seen an atom with my own eyes. Have you seen an atom with your own eyes? No, so that's like phlogiston. Has anybody seen phlogiston? So, being a scientist, you say, okay, I have never seen phlogiston. Prove it to me. Prove to me that there's something called phlogiston. Well, I've never seen atoms, so prove it to me that there are atoms that exist in nature. And what could you offer as proof that atoms exist? Think about it for a moment. Let me do something really quick. So Diana, you have some proof. Law of conservation of mass, exactly. Yeah. Well, actually, electron microscope could, yeah. Nowadays, there's plenty of proof. There are no skeptics nowadays because there's overwhelming proof that atoms exist. I mean, you can see them with an electron microscope. You can see, well, a scanning electron microscope. There are different levels of electron microscopes. You can see them with X-rays. You can manipulate single atoms. Single atoms manipulated. In fact, they've spelled out, like with the older scanning electron microscopes, they were able to move atoms to spell out the words, you know, IBM. I don't know if you've seen that. And they made a little figure using that. Maybe I'll just show that to you real quick. Since the proof nowadays is overwhelming. Overwhelming proof. Let's see, they called it the IBM, man. No, I guess it wasn't called the IBM, man. It was called the IBM. Oh, no, I guess they called it the IBM Boy. I forgot. These are made of with single atoms, so they built the logo here, and then they have the child. This should be. There's a movie made with single atoms. I should get rid of this. Well, anyway, so this is the world's smallest movie, A Boy and His Atom, something like that. That's made with single atoms. Yeah. All right. So nowadays the proof is overwhelming. This is how that works. You know, these microscopes work here. And so nobody is skeptical anymore about the existence of atoms, but did Lavoisier have a scanning electron microscope? Or tunneling microscope? No. So how did Lavoisier know about atoms? Actually, it turns out atoms came after Lavoisier's time. Atoms came about with another scientist named Dalton. And how did Dalton come up with the idea of atoms? Because, you know, there was a dispute. What's the smallest piece of gold you can have? And the dispute was between two groups. One group thought gold should be, or whatever, you know, it doesn't have to be gold, but we're just going to use gold as an example. One group thought that gold was infinitely divisible, which means the smallest piece is, well, you can just take it and take the smallest piece you can make and then just make it smaller by cutting it in half. And so you could just keep making smaller and smaller pieces infinitely, so you can get an infinitely small piece of gold. Whereas another group said, what is the smallest piece? Well, the smallest piece is going to stop at the atom. Because if you tried to make it any smaller than an atom, what would happen? What would happen if you tried to make something smaller than a single atom of gold? You tell me. Yep, you get subatomic particles. And what are the subatomic particles that you'd end up with? Yeah, protons, electrons, and neutrons. The molecule, actually, a molecule is very interesting. The molecule, you're right, a molecule would be the smallest piece of water you could have, like water or sugar. And so if somebody asks you, what is the smallest piece of water you could have? Well, the smallest piece of water I could have is the water molecule. The water molecule kind of looks like this. It has 2 atoms of hydrogen. Hydrogen atoms are kind of small, and 1 atom of oxygen. And it's formed like this little V here. We call it bent, like that. If I tried to make this smaller, then I'm going to get single atoms. Well, single atoms, I'll get hydrogen atoms and oxygen atoms. Well, that's not water. Water, I have to have it all bonded together. And then if I try to make it even smaller, I'd get subatomic particles. And so I can go from a compound. The smallest piece of a compound would be a molecule, in this case. And then compounds can be broken up into the elements. And the smallest piece of an element is the individual atoms. And then if I try to break it up into even smaller pieces, I get subatomic particles like protons, neutrons, and electrons here. That's for water. But the smallest piece of salt, there's no molecules of salt. A salt is like what we saw for the mercury. Mercury 2 oxide is a salt. And so the smallest piece of a salt is what we call a formula unit. This is what we call a molecule because it's very discrete here. But in this case, is there a small circle and a big circle that are bonded? It turns out there's not a distinct one. If I look at this small one right here, there are 3 that are bonded to it. I can pick any of those 3. And so the smallest piece of this salt is what we call not a molecule like this. We call it a formula unit. A formula unit. And so that would be the smallest piece of a salt. And there are lots of different salts. So I'll talk about what a salt is. A salt is usually, we'll probably need a little bit more chemistry to talk about what salt is. Okay, so these are substances. So for substances, the smallest piece of an element is the atom. If I try to break it into smaller pieces than that, it's no longer gold. For a compound, substances can be an element or they can be a compound. For a compound, I have 2 types of compounds. One type of compound gives the smallest piece as a molecule, a discrete unit. This unit has 2 hydrogens and 1 oxygen atom bonded together to form a discrete unit. For the other type of compound, like this salt here, the smallest is not discrete in the sense that I could pick any one of these little ones and any one of the big ones here to pair up, and it's called a formula unit. That would be it. We'll talk more about this later, but just to get you the idea now, that's what we're going to be doing. Okay, so going back to this, atoms came well after Lavoisier. Lavoisier didn't propose the atoms. You know how people decided between these 2? The way people decided between these 2 is water, or air, or whatever. Water has 2 hydrogens and 1 oxygen. If matter were infinitely divisible, so you can get smaller and smaller and smaller pieces, then it doesn't make sense, because can't we have, let's say, in that case, if matter were infinitely divisible, couldn't we have, let's say, H2.1, just a little bit? Let's say, I like my water a little bit rich in hydrogen, so I want my water just to have a little bit extra hydrogen to give me that kick, Is that going to be possible to have a little bit of hydrogen enriched water? Or maybe you're the type that likes oxygen enriched water. So maybe rather than having 1 oxygen, I'm going to have 1.1 oxygens and make my water a little bit enriched in oxygen. Is that something that's viable? Well, that seems like it would be viable if matter were infinitely divisible. We should be able to do that, but matter's not infinitely divisible. And so there are clues as to this. This is one of the results that came out. But the clue for the conservation of mass, this observation led to the hypothesis that matter consists of atoms. The law of conservation, because what happens in a chemical reaction? What happens in chemical reactions is you don't lose any atoms, the atoms just become rearranged. And so atoms came from this. This was the proof. The proof. They didn't have the sophisticated instruments, they just had this as the proof for atoms. And the hypothesis eventually turned into a theory. What a hypothesis is this is your tentative, detailed, or fundamental description. Tentative, fundamental description of what? It's a fundamental description of your law or observation. A theory is, it's undergone testing. And so your hypothesis has been tested and subjected to heavy scrutiny and criticism. And once that happens, then it gets widespread acceptance. So this is accepted. Fundamental description. So one, theory has to do this. It has to be widely accepted fundamental description. So atoms seem to do that. And two, it should be able to predict new observations, unforeseen observations. And so in this case, it predicted a new law. Let me just say. And the new law that it predicted was something called the law of multiple proportions. This is what the prediction came out to. I'm jumping ahead because of this video that they showed. The law of multiple proportions says that water is H2O. It's not H2.10, or it's not, you know, any other number, 1.9. Let's say you're on a hydrogen restrictive diet, and so you want less hydrogen, hydrogen 1.90. It's not this, it's not this. In other words, law of multiple proportions says it has to occur in whole number ratios, small whole number ratios like this, because we have these discrete units called atoms and not some paste that we can paste on hydrogen here and oxygen on there. Okay, is that clear? If it's not clear, what you do is you go back through it. You know, you go back through it and over it. And if it's still not clear, you can ask me, you know, after a break, you know. Let's take a break right now. And then we'll start up again. So we'll take another, let's say 15-minute break. We'll start a little after the hour here. And then go back through this and then see if you can make sense out of it. Okay. All right. I'm going to stop the recording to break up the videos so they aren't too long.